Okay, so we have 12.5 here, which is on absolute maxima and minima. So the definition of absolute maxima is if f of c is greater than or equal to f of x for all x in the domain of f, then f of c is called the absolute maximum. Similarly, the absolute minimum is defined as if f of c is less than or equal to f of x for all x in the domain of f, then f of c is called the absolute minimum. So this basically says that if you have some value of your function, which is greater than all of the other values which you could possibly get from your function, then it must be an absolute maximum. If you have a value which is similarly less than all the possible values which you get out of your function, then it must be an absolute minimum. So these are just the general definitions of what they are for absolute extrema, both the maximum and the minimum. We can take a look at the extreme value theorem, which says that on a closed interval, AB, of a function, f, which is continuous, it'll have both an absolute max and an absolute minimum. So this means that for any closed interval that you pick on a continuous function f, or for in particular an interval of f which is closed, which is continuous for that interval, you're able to pick, or you're not able to pick specifically what the maximum are, but you're able to find that there is an absolute max and there is an absolute min. And so if you're looking for them, those absolute extrema by theorem 2 would be on critical numbers or endpoints of your interval that you're looking at. And so theorem 2 specifically states that it's the locating absolute extrema theorem. And just basically saying that your critical numbers or your endpoints are where those absolute extrema will occur. So if you had that closed interval AB in theorem 1, you would test A, you would test B, and you would test all of the critical numbers that were in that interval. And that would give you all the potential values for your absolute max or your absolute min. And so that's how you would try to find them. And that's the process. Let's take a look at the second derivative test for extrema. So in all of these cases, we're going to have f prime of c equal to 0. We can take a look at examples where f double prime of c is positive. This means that the graph is concave up. This also means that your f of c must be a local minimum because you have a positive second derivative and a 0 first derivative. So that means that the slope is 0 and the concavity is up. So your values of your function are decreasing as they reach C and then increasing after they leave C. So you have the local minimum. The same idea applies with if you have f double prime of c being negative, then your graph is concave down and you would have a local maximum because values of your graph would be increasing until they reach C, and then they would be decreasing after they reach C. So you would have it going up and then going down, which is the hallmark of a local maximum. Now we can also take a look at f double prime of c being equal to 0. Graph is neither concave up nor concave down, so we have no real indication on the maximum or minimum status for this particular point. So it doesn't apply for this particular test if we're looking at the second derivative of c being equal to 0. All right, and then we have theorem 3 that we can talk about, which is mentioning that on a continuous open interval I of f with one critical number c and I, we have two potential situations that we can get out of that, which would be useful for this particular critical number that we're looking at. If our f of f prime of c is equal to 0 and our f double prime of c is greater than 0, then our f of c is an absolute minimum. Now, if we have the same situation, where f prime of c is equal to 0 and f double prime of c is less than 0, then f of c is the absolute maximum. And so these two situations are more or less just examples that can kind of be drawn from the previous table that we were looking at. But it's on a particular interval where there's only one critical number for this particular theorem. And so that one critical number implies that we can test this point as well as the endpoints, and we'll know from how the function is shaped with that one critical number that there's no change in the second derivative on either side of that critical number. And so that critical number allows us to sort of say that there's no other points which can reach the same either minimum or maximum as what this c value has, or this f of c value has. And so that's how you can kind of think about the results from this particular theorem and why they are the way they are. And if you plot them out, you can kind of tell more about what I'm saying with regards to this. But they look like small little either cups or humps from the way that the graph is kind of written out. And so that's why this theorem works the way that it does, because that single critical number indicates to you that you have this particular situation. All right, and so that's the end of this section. And I'll see you for the next one on optimization here in a bit.